You see, as discussed previously, we saw how the gamma and z specifications they can be used to map one another. So if you have gamma specification, you can find what is z. So for example, over here you have a circle, a unit circle of gamma equal to 1, which implies you don't have any real part. It's purely reactive, so it is of the form 0. It means the load is of the form 0 plus jx. Okay, and if jx is positive, that means you are in the upper half of the gamma plane. If jx is negative, okay, or here, then the load is capacitive, so you are in the lower half of the gamma plane. So this implies that this is a constant radius circle of unit magnitude, implying r equal to 0. That means the real part of the gamma is 0. The real part is 0, and only x is being varied. Okay, and this has another implication that if you are going to have different r's, okay, constant r's, you're going to have constant real parts, okay, that is constant, and you're going to vary x, then you're going to get a series of circles, okay, series of circles which may start with the open circuit conditions, and from this point on, with a variable r, with a variable radiuses on the real axis, you have something like this, okay. So it's going to grow like this. This is something like this, and then it goes like this, okay. So the maximum is gamma equal to 1 circle. So let's have a look over here. You see what happens is that you see for every value of r, there's one of the resistance circle. Just like you have this for r equal to 0. The resistance circle for r equal to 0 is a unit circle in the gamma plane. Isn't that right? This is what we saw earlier. So for r equal to 0, this is what it means by gamma equal to 1. So you see that for gamma equal to 1, we have this, the real part of the load is 0. Okay. So this is purely reactive. So all points, you see, this corresponds to pure reactance, but all the points inside the circle, they map to the impedances with positive non-zero R. So that means inside of this circle, we have non-zero R. We have R which is positive, also is non-zero. Okay. So for non-zero and positive R, we will have circles of different radii less than this. Of course, this is R equal to 0, and starting with a circle of radius 0 over here. This circle is 0, which means infinite or open circuit conditions at the load. So for every r, there is one resistance circle, and this resistance circles for r equal to 0 is the unit circle. So in the gamma plane, if you're going to plot gamma as which has the real part and then imaginary part jx, r is a constant and x varies. Okay, so you have constant radius for this circle. You have this is a constant circle. This is a constant resistance circle over here. Then you have another constant resistance circle over here, different radius along the real part. Okay, and this is another resistance circle over here, and then this is gamma equal to 1, and that's the limit, because you can't have gamma greater than or equal to 1. You can't have reflected power more than the incident power over here. So you get a family of those resistance circles, okay, inside gamma equal to 1. So this line of the real, this is real of gamma equal to 1. This line becomes the asymptote. Okay, similarly you have another asymptote. If I would say this is the real part of gamma, which is -1. Isn't that right? So this part is, you see, look over here, this is -1, 0, this is short circuit, this is open circuit. So quite safely I can write this point as in terms of gamma, because this is imaginary gamma, this is real gamma, so this is um, 1 plus j0. Similarly over here, what does this point correspond to? Real part is -1, and this is gamma. Okay, so I'm writing this for gamma. So this is gamma over here, and then I have another gamma over here, which is -1 plus j0, because we are on the real axis. Real of gamma is minus j0. So this implies short circuit conditions, okay, and this implies open circuit conditions, okay. So you're moving from the circle. So for example, the resistance circles, they are emanating for r equal to infinity. they are emanating from the right hand side. It's a circle of 0 radius at point gamma equal to 1 plus j0, you see, but it emanates from here, open circuit conditions, and then the radius, it goes on increasing and increasing, and that gamma equal to 1 is the limit. So these 2 points becomes the asymptote of the constant resistance circles. Okay, they have a constant radius along the real axis, but the x is varying. Okay, so this part, the measuring part, is varying. Similarly, likewise, if you're going to rotate this, I mean, there is a you see the 90-degree transformation. So these solid lines are your constant resistance circles. Uh, you can have the reactance circle as well. So what would you do is, it's the other way around. Instead of plotting constant R, you vary R is varying, and you take X as a constant. Okay, so likewise, if you're going to plot gamma R plus Jx on the gamma plane, real and imaginary parts, you will get reactance circles. They are centered on the line gamma equal to 1 over here, you see. So instead of being centered at the at the real axis of gamma, you have these reactance circles that are centered at real gamma equal to 1. Okay, and this is just like, these are the same circle, but just like they are rotated in a clockwise rotation of 90 degree, produces from resistance to reactance circle, and these reactance circles are shown as in the broken lines. So you see again over here, they're centered at the real gamma equal to 1. Okay, why? Because you see x is constant. Okay, so just like over here, the resistance was constant on the real axis. So the resistance, if you see of this, for example, of this circle, you should see the resistance of this dotted circle. This is the dotted circle, and on the x-axis, or so on the y-axis over here, the resistance is the radius is a constant. Similarly, the radius of the large circle is like this. So let's call this R1, let's call this R2. So it's just a rotation, 90-degree rotation of these circles over here. Okay, and these are constant reactance circles, and R is varying. Okay, but X is constant. So X is constant over here, but R is varying. So R, you see, is a variable. The real part is the variable, and it is centered on gamma equal to 1, and it's tangent to the line imaginary gamma equal to 0. Okay, so this is tangent to this is your gamma, the imaginary gamma equal to 0. This is the tangent, and that's the imaginary of gamma, right? So it's just a rotation. The resistance circle is a 90-degree transformation or rotation of the circles. So these circles are shown in the figure below, so you can see this rotation. But usually in Smith chart, if you are going to trim the circles outside gamma, you don't have anything outside of gamma equal to 1. You're going to consider the circles inside gamma equal to 1 for passive resistances, or for load resistances who have non-zero real part. Okay, and you are going to, if you want to locate, for example, you have a load GL which has a real part, let's say, which has a real part, let's say RL. This is equal to RL plus JXL. Then what you're going to do is you're going to use a chart like this. Okay, and if you consider this part of the gamma plane, this is Smith chart, right? So what you do is, these are the reactance circles. Okay, you understand, these are the reactance circles. So they're going like, these are like arcs. Okay, and similarly you have more arcs, or like this. Okay, like this, it goes on. So what happens is that, for example, you're going to use this for XL. You are going to look at over here. Okay, what is these X values? Normally, commonly this Smith chart is normalized with respect to the center impedance Z0. So if you have normalized this, then you normalize the reactance part as well, and you see where does the resistance circle and the reactance circle intersect. Okay, for example, this could be your ZL, this could be your ZL. Okay, you will see what a resistance circle is that corresponds to the load, the positive part of the load, and you're going to look at the reactive part, where does it intersect, and that's how you plot the load impedance. Okay, for example, this is a Smith chart. So if you're going to trim the circles, leave only the portions within gamma equal to 1, so corresponding to the passive impedances. The impedances of the real part is positive, non-zero, Then you're left with a very useful piece of a graph paper, which you might have come across in the microwave and antenna engineering courses, which is famous as Smith chart. And you see these are these are the reactive arcs. Okay, these are the reactive arcs over here, and these are in the inductive region. Okay, so these reactive arcs are positive. So if you have Gx for these reactive arcs as greater than 0, and then you have the reactive arcs which are emanating from the open circuit. So this is the open circuit conditions. Okay, this is the short circuit conditions, and this is my gamma plane. So you see, basically Smith chart is like a polar plot of a gamma. Gamma is again it's a complex quantity. Okay, so you have both the imaginary and real parts of gamma. It can be written as such. The theta, okay, theta being the phase of the reflection coefficient, because your load can be complex, consisting of a non-zero part of the. If you're going to consider the gamma at z equal to 0, well, that's the case. Okay, and if ZL is complex, that means gamma is complex. Okay, so it has both real and imaginary parts. So it's like a polar plot of gamma, and this is the real part. So you have the upper half plane is inductive, then there's capacitive. So if you have the load impedance, you see where does it intersect? It intersects over here. It intersects over here. What is the load impedance that is being specified? Okay, so that's how you locate ZL, and then from ZL, you know there is a one-to-one mapping between gamma. Okay, so you find the reflection coefficient from this one-to-one mapping of Z and gamma. So you see the circular R and X axis on the Smith chart. They allow you to locate the gamma point that corresponds to J. So it corresponds to the load impedance Z. Okay, so there is a one-to-one mapping between gamma and Z. So once you have gamma, you should have. If you had Z, then you have the reflection coefficient. Okay, so we have seen already that when we located an impedance on the gamma plane, so whatever the impedance is, that is the intersection of the constant resistance. So for the resistance, you're going to consider the those resistive circles. Okay, those are the resistive circles, the maximum being equal to 1. So this circle is gamma equal to 1, which implies r equal to 0. Okay, so otherwise for non-zero r, you look down inside those circles. Um, so we have already seen that when we have located the impedance on the gamma plane, we can find how that impedance is modified by the length of the transmission line. So characteristic impedance Z naught is the same as Z naught used to draw the chart. So what you do is you rotate the point clockwise around the origin. So how you're going to, for example, if you know this is your load impedance, okay, let's call this point as load impedance just for the sake of explaining how you're going to transform the impedance, and you have to find what is my Z prime. Okay, that means you are going to rotate your Smith chart clockwise in a direction. This is towards the generator side. So towards the generator, which means you are going down the line. Since the load is at, you understand, the load is at Z equal to 0, right? Here, this is your transmission line. Okay, this is your transmission line, and you are at the load side, and this load is at Z equal to 0. Okay, Z equal to 0. Here's your layered load ZL. Okay, which could be inductive. If it is inductive, then your load is on the upper half lane. If it is capacitive, then you are looking at the plot of the load in the lower half lane. So this is your ZL, which is in general equal to R plus JX. Okay, R plus JX. And if you know how to plot this on the locate this on the Smith chart using the constant resistance circles, between you're going to locate this by the intersection of resistance circle and the reactance arcs, and that cross point is your ZL. Then you're going to rotate this clockwise. You're going to go downwards from this point Z equal to 0 to, let's call this the generator, where the generator is, and let's say the transmission line is of length L. So this is Z minus L. Okay, if this is equal to 0, then you're going down the line. So this is Z minus L. So you're going to traverse this. So for example, there is some point over here, okay, and that could be your Z prime. But you need to understand that what is the from the center, you're going to draw a line like this, and then from this point we are going to know, you will know what is the electrical length is. So how much KL in degrees, okay, you are going to uh, how much phase shift you need from this point is equal to 0 to, let's say, small l, to traverse or go down the line towards the generator side. So you're going to move towards the generator in a clockwise fashion, and you're going to find what is the impedance Z prime. Okay, that's the Z prime. Okay, so all the information that you required is KL. Okay, you need KL, and L is known because that's the physical length of the transmission line. So what we are doing over here is simply rotating the point clockwise around the origin. Okay, the origin is over here by an angle equal to twice the electrical length of the line. Okay, so this is twice, this point is actually twice the electrical length of the line. Okay, so the values of R and X corresponds to the rotated point that can be read off the charts R and X axis. We can also use the chart to find how an impedance is modified by adding series R or series X. Okay, so what's going to happen over here is you're going to add more reactance. Okay, possibly this goes up, and if you're going to add more series resistance, this is going to move. You have to move to another circle. Okay, for example, if you're going to add more series resistance, we are going to move along like this. So you might want to add you have to go to another resistance circle that indicates higher series resistance that we are going to add. So in this operation, the Smith chart can be considered something of a calculator. Okay, so note that the Smith chart can also be made with G and B axis. So you see, you have Z as R plus JX, but if you are interested in the want to treat this as an impedance chart, you have to rotate this chart, because you see the 1 over R is what G conductance, and then you have your JB, which is the susceptance part. So that's your admittance. If you want to treat this as an admittance, then you have to rotate this. You have to look at the conductance and susceptance circles. So there is a phase shift again of 90 degrees from here. Resistance constant. You need to look at the constant conductance circles and constant susceptance circles. So as you might guess, these produce G circles and B circles. Just like before, you have constant resistance circles. Okay, so you have constant conductance circles. These are the straight lines, and then there are dotted lines that show the susceptance, or the B part. Okay, this is your B part. That's the G part. Just like before, what we have seen in the transformation, which you recall over here. So these were your resistance circles. Okay, constant resistance circle, and then you are going to transform them for constant reactance circles over here. Similarly, over here you have constant conductance and constant susceptance circles. So, for example, over here, these are emanating from the other side. Okay, over here we had open circuit condition. Now it's the reverse. This is short circuit, and then this is open circuit. Okay, this is G, because G is 1 over R, so it's the other way around. Okay, it's the reciprocal. G is 1 over R. So open circuit and short circuit are switched. Okay, for example, over here, see, it was emanating from here, this side, from the right hand side, which was the open circuit. Now here, this is emanating from the left. Okay, so that's you're going to treat as the G. But in terms of Z, it is still the same. Okay, in terms of Z, it's still the short circuit point. So you can use this as an impedance chart. As an impedance chart, you can use this as you can use the gamma plane as an impedance chart. You can use this as an admittance chart if you so wish. Okay, you can have constant conductance susceptance circles. Sometimes the Smith chart, it contains G and B circles, both G and B and R X circles. So it's a full-blown Smith chart. This is a full-blown chart which is quite dense, which is shown below. But again, it depends on your choice. If you want to make the calculations with both impedance and admittance, for, you see, if you want to, you're designing a stub matching, for example, if you have to add more series of shunt stubs and you have to move along the constant resistance circles, you have to rotate. You don't have to rotate it again and again, but you can use these both G and B and R plus X circles to your advantage. So remember, the Smith chart is actually a rectangular plot of gamma. So the x-axis there is the real and the y-axis is the imaginary part of gamma. So because only the area inside gamma equal to 1 uh, is used, the Smith chart resembles the polar graph. So we are using this inside gamma equal to 1. So we are using this for gamma is less than equal to 1. And indeed, when we rotate a point around the origin to how a transmission line modifies an impedance, we are using it in a polar fashion. Okay, so sometimes the Smith chart is scaled for specific characteristic impedance of the transmission line, usually 50 or 75 ohms. So you're going to normalize this by the characteristic impedance. Other charts are normalized. R equal to 1 circle would be 50 ohm circle then. So we are dealing with a 50 ohm cable, etc. If it's 75, then R equal to 1 corresponds to 75 ohms. So this is Smith chart with both R, X, and G and B circles. This is a full-blown, very dense Smith chart. So if you wish, you can do it for more complex calculations. You can use it for more complex calculations like impedance matching for maximum power transfer and so on. So that's about the constant gamma circles. Okay, that's how you derive the Smith chart from the constant gamma or constant reflection function circles.